You type a quick request into your phone, asking for the fastest route across town, or maybe a poem about a sad robot. And less than a second later, the screen lights up with a perfectly formed answer. The transition from your everyday question to that complex response happens so fast, it feels a little magical. It naturally makes you wonder what exactly is happening in there. Is there a hidden consciousness inside the device? A tiny digital brain quietly weighing the options before it speaks? When we think about thinking, we picture our own minds. Human thought is a messy, beautiful product of billions of years of biological evolution. We rely on intuition, sudden flashes of insight, and a lifetime of lived emotions to make our choices. An AI operates on entirely different principles. It relies on high-speed, hyper-logical mathematical computation. There is no self-awareness, no intuition, and zero genuine understanding of the world it interacts with. Instead of a mind, many of these systems rely on a specific digital component called a reasoning engine. This is the structural core that allows the machine to move past simple pattern matching and start actively solving problems. An AI never ponders. It never feels its way. It simply processes. By substituting biological consciousness with an incredibly fast, hyperlogical architecture, it creates a highly convincing simulation of intelligence. So let's look at how that architecture is built. Instead of biological cells and synapses, this digital brain is constructed entirely from code, split into two distinct, highly specialized parts. The first component is the knowledge base. You can picture this network as a massive, static library. It holds all the raw facts, strict rules, and known variables the AI has been fed about the world. Whether it's medical symptoms or city speed limits, this is the raw, unmoving material the system draws from. But a library doesn't work without an active librarian. That's the second component, the inference engine. This is the operative force that navigates the data. It takes your prompt, dives into that static library, and actively links specific pieces of information together. The inference engine applies rigid, programmed logical rules to extract a coherent answer. If the knowledge base is a giant box of scattered puzzle pieces, the inference engine is the mechanism that rapidly sorts through them and connects the exact pieces needed to complete the picture. Machine intelligence is the successful mechanical combination of stored historical data and active mathematical retrieval. To see how this engine runs under pressure, let's give it a concrete optimization problem. We'll ask a GPS system to find the absolute fastest route to the airport. The engine immediately triggers step 1, input understanding. The system strips away the conversational fluff of your sentence and isolates the actionable key concepts. It zeroes in on the words fastest, route, and airport. In step 2, knowledge representation, those isolated words are translated into mathematical coordinates. Look at this geometric node network representing our map. The system flags your exact starting location as one node, highlights the airport as the destination node, and defines fastest as the goal. Now the engine reaches step 3, applying its core logic. Many systems use a data-driven method called forward chaining. The engine begins with specific, observable data, like a patient presenting with a fever and a cough, and expands outward, matching rules step by step until it reaches a logical conclusion. But for our GPS problem, the engine uses goal-driven logic, or backward chaining. It sets the airport as the definitive goal and works backward. It evaluates all the connecting roads, checking each path against the speed limit rules stored in its knowledge base, until it isolates a single optimal route back to your car. Before showing you the map, it runs step 4, contextual evaluation. This is a vital sanity check. The absolute shortest mathematical distance to the airport might be a straight line going right through a solid building. The engine recognizes this intersects an unroutable boundary, discards the impossible path, and instantly reroutes around it. Finally, in step 5, decision and output, the engine takes this verified, logical proof and translates it back into a human-readable format. A blue line appears on your screen, and a synthetic voice tells you to turn left. The entire 5-step algorithmic process happens in milliseconds. It's this sheer superhuman speed that tricks us into believing there's a conscious mind at work behind the screen. But pure logic has distinct limits. Imagine a driver has a passenger in the midst of a life-threatening medical crisis. To reach the hospital, they must decide whether to bypass a red light on an entirely empty street. In this moment, the inference engine freezes. To the engine, a red light is a hard constraint, a mathematical zero that cannot be crossed. It has no way to weigh the zero of a traffic rule against the infinite value of a human life, because it possesses no understanding of what a life actually is. A human driver instantly adapts. We recognize that the spirit of the law, safety, is better served by breaking the literal rule. We use lateral thinking and common sense to navigate scenarios where rules and reality collide. A pure rule-based logic engine is brittle. The moment it encounters a scenario that demands this kind of contextual human understanding, the mechanical process fails. This reveals the clear divide between machines and us. When it comes to speed versus adaptability, machines process massive datasets instantly, but humans effortlessly navigate unpredictable, low-information anomalies. We also see a strict divide between pattern generation and true creativity. A machine's output is a dazzling act of statistical recombination. Human creativity stems from a conscious desire to express a lived experience. And as we saw with the emergency at the red light, there is a gap between following rules and exercising morality. AI can mimic ethical alignment through training, but it possesses no empathy to judge when a programmed instruction should yield to a human need. Pulling back the curtain shows us that AI is an immensely powerful, mechanical logic engine. It requires our human consciousness, our ethics, and our creativity to steer its raw computational power toward meaningful progress.